Today we are going to talk about one of my favorite kind of stories in statistics. It basically deals with kind of some copyright issues, working industry, trying to publish papers, which unfortunately I've had to deal with before as well. But anyways, so far in this course, now we're central limit theorem masters, but we've been dealing always with this kind of condition that our sample size has to be large. But there are certain situations where we cannot gather large samples, either for practical reasons, economic reasons. There are some times when we just we cannot gather more than 30 samples. So what do we do when our sample size is small, i.e. less than 30? Do we just give up? No, unfortunately not in this course, and in academia and science and engineering and basically any other field as well. But instead, we have to use basically a different tool, a different distribution set that we've kind of discussed about previously. We are going to use a t-table, t-test, and the student's t-distribution. So very, very similar, straightforward. We're going to use kind of this expression, which is analogous to our new z expression. And again, now we're dealing with basically sample means. So samples of sample means. So that's what we're going to be working on moving forward. So if you have any questions during an exam or problem set or a problem statement, please let me know and I'll be happy to clarify. So I love telling the story of the student t-distribution. So this student is a pseudonym. So it's a pen name. It's like Samuel Clemens, Mark Twain, all those other good stuff. I think Stephen King also went by a pseudonym or a pen name. But anyways, but basically, student was a pseudonym for an amateur statistician. Oh, that's hard to say. But student was actually William Gossett. So William Gossett was a Guinness brewer. So he worked for Guinness, and he was in Guinness. He was applying already statistical tools and statistical analysis to help improve the brewing process. So again, as an engineer who wants to kind of, again, who's developed this kind of new technique or this new set of analysis tools or this new theory, William Gossett wanted to publish his results, but Guinness obviously did not want him publishing the data because then you could give away all the Guinness secrets that basically the tools that he was already using to kind of improve the brewing process. So instead of fighting against the company and trying to argue for patents and all these other good, this stuff, he basically just published the data anyways under a pseudonym, which was very, pretty bold. Basically, he must have been very confident that if that was found out and he got fired, he could get another job. But kind of a fun story. So he published the data anyways, and so now it's again, it's a little bit disappointing because otherwise it could be known as the Gossett t-distribution. But anyways, just a fun little story here. So this is the t-distribution. So the assumption here is that basically the underlying population satisfies the Gaussian probability distribution, but again, it doesn't matter as long as you're dealing with means. And we're going to introduce a new term called the degree of freedom, nu. So nu is basically just n minus 1, the number of samples minus 1. So the t-distribution, very similar to the PDF. It is also symmetric. The total area is unity. And as our t-distribution approaches the standard Gaussian, or as n becomes large or greater than 30, the two distributions will look essentially identical. So we could kind of see that by looking at our t-table right here. So this is our t-table. So you can see here, we'll talk about alpha in a second as well, but as nu becomes large, as it becomes infinity, you'll see that these values are exactly the same as our z values. But we'll come back to that in just a second. So let's look at now the area or alpha that we see here in this t-table right here is a little bit different from our z value. So the area alpha is between t and t infinity. So whereas previously we had basically our z table probability, we had that we had z equals 0, and whenever we looked at the t-table, we were looking at values from z equals 0 to z equals z, and we got this area. In our t-table, we are going to be looking at something different. So we are going to be looking at basically area from t to t infinity. So that's what that area is giving us there. So what we have to instead do, we have to basically use our confidence interval is going to be 1 minus alpha in order to get this other area here. And that's the probability that the actual area does not fall in the shaded area. So that is going to be our whatever our alpha is, or whatever our confidence interval that we're working with, it's going to be 1 minus alpha. So if I want to find, for example, my confidence interval of 95%, I'm looking at an alpha value of what? 1 minus 0.95, 0.05. So, and I could kind of double check this, right? So I'm looking for a confidence interval of 0.05, 95%. If I go all the way down to infinity, you'll kind of see, actually, if it's a two-sided, we'll get to two-sided in a second, we'll recover this relationship. 95 divided by 2, again, that's what we're looking at in your Z table, right? So if we want 95% of our data, we know that it is going to be that 1.97 value. So it's the confidence interval divided by 2. So 95% divided by 2, that's when we find our, basically that 1.97, because we get the 0.475 in our Z table. Back here in a second. And we can look back at that right here, actually. Oh, it's right here. So for 0.475, right here, that corresponds to a Z value of 1.96. And if we look over here, my confidence interval, which is going to be 95%, so that means an alpha value of 0.05. Divide that by 2, 0.025. Go down here, 1.96 for Z infinity. So everything should hopefully make sense in the world. So all we have to do then is rewrite this expression for a two-sided confidence interval. That will give us essentially this value. And you have a very similar, again, same expression to, again, express where will the true population mean lie at a certain confidence interval. So, or alpha will sometimes be called as the level of significance. So level of significance just means, so if I have a level of significance of 1%, that means my alpha value equals 0.1. And you can now express your precision uncertainty or your precision error like this. And you do the same thing for Z as well. That is the t-distribution. Next time, we're going to do some problems, or a quick problem, and then we'll get into hypothesis testing. So we'll see you on the next one. Thank you. Bye.